Imagine, if you will, the most impenetrable bank vault ever constructed.
Okay, I'm picturing it.
Right. So we are talking like 3-foot thick titanium doors, laser grids spanning every single hallway, and, biometric scanners that check your retinas and your fingerprints.
The whole 9 yards.
Yeah.
An absolute masterpiece of modern security engineering.
Exactly. It's flawless. But then in the middle of the night, the entire system just shuts down. The vault swings wide open.
Just like that.
Just like that. And why? Because somewhere in the, millions of lines of code running that flawless security system, somebody forgot to put a period at the end of a sentence.
Which sounds insane.
It sounds like a terrible trope in a Hollywood heist movie. But in our stack of security research today, it's exactly how the biggest enterprise networks on the planet are being breached.
It really is.
Yeah.
And in the architecture of digital security, that missing period it's a very mechanical reality. Yeah. We tend to visualize cyber attacks as these like high-tech brute force hacking sequences with, green code raining down a monitor.
It's a Matrix style.
Exactly. But the truth found in today's threat reports is, well, it's much quieter. It is usually a tiny, invisible structural flaw that just bypasses the vault door entirely.
Okay, let's unpack this, because our mission today for this deep dive is to decode the modern anatomy of a cyber attack.
It's a great mission.
Thanks. So we are pulling from a massive stack of urgent vulnerability analyses and technical breakdowns from security research groups. We've got stuff from Watchtower Labs, Blackpoint Cyber, Horizon3.ai.
That's some really heavy hitters in the research space.
Truly. And we are going to examine 3 newly disclosed critical enterprise software vulnerabilities to see exactly how threat actors are getting in. But, this isn't just about dense code.
No, not at all.
It is about a fundamental shift in how digital heists are actually pulled off today. We're looking at how they get in, how they hide, and most importantly, what they are stealing once they get inside.
Right. And the real story we are going to see unfold in these sources is the pivot in the attacker's ultimate goal.
Which is wild to see.
It is. Because once they use these mechanical flaws to slip inside, they are increasingly targeting the very AI tools that you, the listener, might be using to do your job right now.
Yeah.
That is the new prize.
So to understand the modern cyber heist, we first have to look at how attackers actually pick the lock.
The entry point.
Right, the entry point. And for that, we start with the mechanical simplicity of just a catastrophic flaw. We are looking at a vulnerability known as CVE 2026-8037.
Rolls right off the tongue.
Oh, yeah. And it carries a 9.8 critical severity score out of 10.
Which is as bad as it gets, practically.
Yeah, a 9.8 is no joke. And it sits inside something called the Progress Kemp LoadMaster. So what exactly is that?
So a LoadMaster is an application delivery controller. It's a load balancer. For you listening, just think of it as the ultimate traffic cop for an enterprise network.
Okay, traffic cop. Makes sense.
Right. It sits right at the network edge, managing all the incoming web traffic and directing it to various internal servers so that no single machine gets, overwhelmed.
So it's right out there in the open.
Exactly. Because it sits at the edge, it is outward facing. It is literally the front door. So any pre-authentication flaw here...
Wait, now you don't even need a password?
Right. Pre-authentication means a vulnerability you can exploit without even needing a username or password.
Wow.
So a flaw here gives an attacker a direct foothold right into the perimeter.
And the specific flaw lives in an API endpoint, right? I think the sources said it was the Access v2 endpoint.
Yeah, Access v.
Which is supposed to handle credential validation when someone tries to log in. And inside that API, there is a function called escape quotes.
Which has a very specific job.
Right, to sanitize user input. It escapes single quotes so that an attacker cannot, break out of a quoted string and inject their own malicious commands.
But the problem wasn't with the escaping itself, though.
It wasn't.
The underlying failure was in how the system handled memory.
Okay, walk me through that.
So when this escape quotes function ran, it allocated a memory buffer. Think of a memory buffer as essentially a temporary parking space in the computer's RAM.
Right, just holding data for a second.
Exactly. It holds the sanitized string of text. But the developers didn't write it to clear that parking space first.
Oh.
Yeah, it just left whatever jump data happened to be sitting in that memory block from, previous operations.
And this brings us back to the missing period from our vault analogy.
Yes, exactly. So in C-style programming, a string of text needs to end with a null terminator.
A null terminator.
Right. It is an invisible character that essentially tells the computer's memory, Stop reading here, the sentence is over.
The period.
The period. But this escape quotes, function never wrote a null terminator at the end of the sanitized string.
So the computer doesn't know where the bumper of the car ends, basically, and it just keeps reading into the next parking space.
Exactly.
Yeah.
Without that terminator, the system keeps reading past the end of the sanitized input, right into whatever data happens to be sitting next to it in memory.
Which was the junk data you mentioned.
Well, here's the mechanical trick. An attacker can actually control what sits in that adjacent memory space.
Wait, how did they do that?
They do this by stuffing extra JSON keys into the very same API request.
Okay, and JSON keys are just simple text labels used to organize data in web requests, right? Like labeling a piece of data, username or password.
You got it. So the attacker sends dozens of extra, completely unnecessary JSON keys packed with malicious shell commands.
Okay, I want to make sure I'm visualizing this correctly for everyone. It's like a bouncer checking your ID at the club.
Okay, I like that.
So the bouncer reads your name, but because there's no period at the end of your name, he just keeps reading aloud from the VIP list in his hand. And he eventually reads an instruction that says, like, let the 50-piece marching band in. And because he's just blindly following the text, he executes the command. By forcing the system to overread its own memory, the attacker can execute commands as root.
Granting them total system control.
Total control.
And remember, no valid credentials are required at any point in that chain.
Wait, okay, but if the architecture fundamentally fails to manage memory at the network edge like that, don't they have to rip out and replace that entire authentication module?
You would think so.
I mean, a 9.8 severity flaw rooted in memory allocation, that sounds like it requires a massive overhaul.
What's fascinating here is the sheer minimalism of the patch.
Really?
Yeah. The researchers at Watchtower Labs analyzed the patch diff.
Which is the process of comparing the old vulnerable code line by line to the newly patched code, right?
Exactly, to see what the developers actually changed. And Progress made exactly two modifications. Two. First, they swapped the memory allocation function from one that leaves the buffer uninitialized to one that zero fills it.
Meaning it actively sweeps the parking space clean before using it.
Right. And second, they explicitly added that missing null terminator after the escaped output.
So literally 2 lines of code closed a direct path to root access. That is wild.
It is.
Now, I know Progress noted there haven't been any reported attacks exploiting this specific flaw yet, but there is a working proof of concept out there.
Which is basically a public instruction manual on how to execute this JSON key stuffing.
Right, and that was published by Watchtower Labs on June 29th. And context really matters here because Progress is the same company behind MoveEat.
Oh, yeah, the MoveEat transfer software vulnerabilities.
Back in 2023, those flaws fueled a massive global exploitation campaign by the CallVRP ransomware group. So when a 9.8 severity flaw drops for a Progress Edge device, the security community takes it very seriously.
Absolutely. But, breaking the lock at the front door is really just the first step.
Just getting in.
Right. If threat actors want to do lasting damage or extract serious value, they need to move from that edge load balancer into the internal systems of a company.
And that requires a completely different type of exploit methodology.
It does.
So let's follow that progression because our sources highlight the shift perfectly. We are moving from the network edge to the internal financial organs of an enterprise.
We juicy stuff.
Yeah. Our next source details another 9.8 critical vulnerability, CVE 2026-46814.
Another 9.8?
Another one. This time, it is an Oracle e-business suite, specifically inside Oracle payments. This is categorized as an improper privilege management and authentication flaw.
Which essentially means the system gets confused about who is allowed to do what.
Exactly. And the National Vulnerability Database confirms this allows an unauthenticated attacker with network access via HTTP to completely compromise and take over Oracle payments.
And unlike the LoadMaster vulnerability, where, no attacks have been reported yet, this Oracle flaw is actively being exploited in the wild.
Right now,
a cybersecurity group called Diffuse Cyber actually observed threat actors attacking their Oracle e-business honeypots.
And honeypots are essentially decoy servers set up to monitor hacker behavior, right?
Yeah, digital traps. And they saw attackers hitting these decoys over a single weekend.
Okay, I need to pause on that, though, because the sources specifically state there is no public proof of concept code for this Oracle flaw.
No public instruction manual.
Right. No security researcher has published a guide on how to break in. So if there's no public instruction manual, how are hackers already actively attacking decoy servers with it?
It's a great question. If we connect this to the bigger picture, It highlights a profound acceleration in the cyber arms race,
How so?
specifically around a technique called patch reverse engineering. Threat actors, they aren't waiting for security researchers to publish a helpful proof of concept anymore.
They're doing it themselves.
They are actively monitoring the security patches released by companies like Oracle. The moment a patch drops, highly skilled groups download the updated software and use that diffing process we just talked about.
Ah, comparing the old and new code.
Exactly. They compare the new compiled machine code against the old version. By seeing exactly what Oracle fixed, they can deduce the exact nature of the vulnerability.
Wow.
And then they just write their own custom exploit for it, entirely in the shadows.
So the very act of a company releasing a fix becomes the map the attackers use to find the vulnerability in anyone who hasn't applied the update yet.
You nailed it. And they are building these weapons faster than most IT departments can schedule a maintenance window to apply the patch.
Which is terrifying.
Furthermore, they aren't just exploiting one bug and, dropping ransomware immediately to make a quick duck anymore.
They're playing the long game.
They are chaining vulnerabilities together. Our sources draw a clear parallel to another recent missing authentication zero-day flaw, this one in PeopleSoft Suite, which led to a massive data theft at the automaker Nissan.
Oh, I remember that. That breach compromised payroll records, bank details, and social security numbers across multiple countries.
Right. And Jake Knott, a principal security researcher at Watchtower, had a very specific observation about that PeopleSoft attack that perfectly applies here.
What did he say?
He pointed out that it wasn't just another trivial single request vulnerability. He said, and I quote, "The attack chain is considerably more involved, combining multiple vulnerabilities to plant a malicious file that doesn't execute immediately, but waits until the server restarts."
Waits until it restarts.
Yes. The mechanism of waiting is critical. They're planting logic bombs that sit dormant.
Okay, walk me through what happens when it restarts.
So when you restart a server, the system flushes its active memory and runs through a series of automated startup scripts.
Just normal housekeeping stuff.
Right. But by chaining these vulnerabilities together, the attackers embed their malicious code directly into those routine startup processes.
Oh, wow.
Yeah, this means when the server eventually reboots, the malware is executed natively by the operating system with system-level privileges.
Because it thinks it's supposed to run it?
Exactly. It completely bypasses real-time behavioral detection because the system thinks it's just running its normal boot sequence.
That is so sneaky.
Knott points out that this kind of multi-vulnerability chaining suggests threat actors who understand the enterprise software just as well, if not better, than the engineers who deployed it.
So they break in, they embed the logic bomb in the startup sequence, and then they just walk away. They wait for standard IT maintenance, like a routine server restart on a Sunday night, to actually trigger the exploit.
It completely upends how organizations need to approach network defense. Knott strongly urges companies to adopt an assume compromise mindset,
Meaning?
meaning patching your systems is no longer a silver bullet.
Yeah.
If you apply an Oracle patch a week after it comes out, you have to assume that someone reverse engineered that patch on day 1, breached your system on day 2, and established persistence in your startup scripts.
So you cannot just patch the vulnerability. You have to actively hunt through your network architecture to see if someone is already inside waiting for that reboot.
Exactly.
So we know the entry point at the edge, and we see the patience of the long con once they get inside the network. But what are they actually doing once that server restarts? Like, what is the payload they're looking for today?
The payload is total, unfettered access to the most valuable workflows in a modern enterprise. And this brings us to the most alarming vulnerability in our stack today, which targets the very tools administrators use to manage the network.
We're looking at a maximum severity flaw, a perfect 10.0 CVSS score.
You can't score higher than that.
Nope. This is CVE 2026-48558, affecting a platform called SimpleHelp. SimpleHelp is remote monitoring and management software, commonly known as an RMM.
Right.
And IT teams use RMM platforms to remotely control computers across an entire company, deploy software updates, and troubleshoot employee issues. It is the master control room.
And the flaw Horizon 3.ai, discovered in SimpleHelp, is an authentication bypass in the OpenID Connect, or OIDC, flow.
Okay, OIDC.
Yeah, OIDC is a standard protocol that different systems use to verify a user's identity.
Let's break down how that bypass actually functions mechanically. Because OpenID Connect is essentially like a digital notary public.
That's a great way to put it.
When you log into a system using OIDC, you aren't handing the server your username and password directly. You are handing the server a token, a digital document, that has been cryptographically signed by a trusted identity provider, verifying who you are.
Right, but the vulnerability in SimpleHelp was that the server's validation logic was fundamentally broken.
Oh, broken.
Well, it was accepting these OIDC tokens without actually verifying the cryptographic signature.
Seriously?
Yeah, an unauthenticated attacker could simply forge a token, write in whatever identity claims they wanted, like, say, assigning themselves the role of technician, and submit it.
So they just write their own hall pass.
Exactly. Because the server failed to check the notary stamp, it just accepted the forged document at face value and granted the attacker a fully authenticated administrative session.
Okay, here's where it gets really interesting. Because a standard defense against this is multi-factor authentication, right? MFA.
Right, you'd think MFA would save you.
You might assume that even with a forged token, an MFA prompt would stop the attacker in their tracks. But the sources detail that even when the SimpleHelp server is strictly configured to enforce MFA for all technicians, the attacker still bypasses it completely.
And the mechanism it's almost comical.
It really is. On the very first login of this newly forged technician account, the system's logic helpfully prompts the user to self-register their own MFA device.
It asks the hacker for their phone number, basically.
Basically, the attacker simply links their own authenticator app to the forged account. The security control effectively weaponizes itself to protect the attacker's access.
It's brilliant in the worst way. And once they establish that authenticated technician session on a publicly accessible RMM server, the real damage begins.
What happens next?
Blackpoint Cyber documented the attack chain from this point forward. They observed the threat actor using this trusted administrative channel to deploy 2 previously unreported malware families.
And those are Taskweavers and GenStealer, right? Let's examine the mechanics of those payloads, starting with Taskweaver.
So Taskweaver operates as a heavily obfuscated Node.js loader. Node.js is a runtime environment that allows JavaScript to execute directly on a computer's operating system,
Right.
rather than just inside a web browser.
Right.
The malware drops onto the infected system, disguised as a mundane file. It's usually named something like jQuery.js, and it just runs quietly through the node executable.
Hiding in plain sight.
Very much so. What makes Taskweaver sophisticated is that it doesn't just execute a fixed list of commands. It fingerprints the infected system and establishes an encrypted, reusable communication tunnel back to the attacker's infrastructure.
Oh, wow.
It acts as a modular beachhead. It allows the attacker to dynamically pull down and execute new JavaScript payloads with elevated privileges whenever they want.
And through that secure beachhead, they deploy the second stage payload, which is GenStealer.
GenStealer.
Yeah. The sources detail exactly what GenStealer is designed to siphon out of compromised Windows, macOS, and Linux hosts. And it goes far, far beyond just grabbing browser history or saved passwords.
Oh, absolutely.
It specifically targets the foundational infrastructure of cloud computing.
GenStealer is hunting for the keys to the modern DevOps environment. It aggressively scrapes configuration data and authentication tokens for AWS, Azure, Google Cloud, and Oracle Cloud.
He wants everything.
Everything. It targets HashiCorp Vault, Docker authentication, SSH keys, and GitHub command line data. And the mechanism it uses on Linux systems is particularly aggressive.
I read about this.
Yeah, it doesn't just look for save files, it actively reads virtual files provided by the operating system,
Yes.
specifically procbit CND line and procbit environ.
Let's clarify what those files are for the listener, because that mechanism is crucial. In Linux, every running process has a virtual directory in the proc folder that stores live data about that program. The environ file contains the environment variables passed to the program when it started, and developers frequently and often mistakenly pass sensitive API keys or database passwords in the command line when they spin up a new process.
It happens all the time.
So GenStealer actively scrapes that live memory to steal credentials while they are actually being used.
And once GenStealer gathers all this infrastructure data, along with cryptocurrency wallet data, it packs it into an archive.
Yeah.
It then encrypts that archive using AES 256 GCM encryption.
Which is military-grade encryption.
It is. And they use it specifically so that when the stolen data is exfiltrated out of the building, it looks like completely random, unreadable noise to the company's network defenders.
They can't see what's leaving.
Exactly. But amidst all of this cloud architecture theft, the research sources highlight one specific target that represents a massive shift in attacker behavior.
Yeah.
They are hunting for AI credentials.
This is the pivot we mentioned at the start. GenStealer is explicitly engineered to target configuration files, authentication tokens, session data, and project histories associated with Anthropic Claude, Google Gemini, OpenAI Codex, and several other AI coding assistants.
And this raises a really important question.
Why are they doing it?
Exactly.
Yeah.
Why are threat actors dedicating complex malware just to steal your AI assistant session token?
Right.
The answer lies in how deeply embedded AI-powered platforms are becoming in enterprise workflows. If you consider the day-to-day life of a software engineer, they are feeding their AI assistant proprietary source code to help debug it.
Yeah, all the time.
They're uploading database schemas to generate queries. They're pasting in architectural diagrams and occasionally live API keys.
So the AI assistant holds the complete context of the company's most sensitive intellectual property.
Exactly.
By compromising the remote monitoring platform, like SimpleHelp, the attacker gains a trusted administrative channel, that single OIDC authentication bypass cascades.
The domino effect.
It allows the attacker to reach down into a developer's workstation, steal the session tokens for their AI assistant, and suddenly the attacker can query the AI to understand the company's proprietary code base.
They don't even have to read the code themselves. They just ask the AI.
They can simply read the history of what the lead developer has been working on for the past 6 months.
The security researchers summarized the threat perfectly. They said, credentials accessible from a developer or administrator workstation may provide entry into production infrastructure, build pipelines, source code repositories, deployment platforms, cloud tenants, and customer environments long after the original endpoint has been contained.
It is the ultimate supply chain attack, but it is localized entirely within your own organization's internal workflow.
The threat is so severe that CISA, the U.S. Cybersecurity and Infrastructure Security Agency, they immediately added this SimpleHelp vulnerability to their known exploited vulnerabilities catalog.
Which legally mandates that federal agencies patch it without delay.
Right away.
So what does this all mean for you and the networks you rely on? We started this deep dive looking at a tiny mechanical error in a load balancer.
That missing null terminator.
Right, a single missing period that left the front door wide open by failing to manage a memory buffer. We traced how attackers are no longer relying on public guides, but instead reverse engineering security patches to chain vulnerabilities together in systems like Oracle.
Planting logic bombs that wait silently for a routine server restart.
Exactly. And finally, we saw the ultimate endgame in the SimpleHelp exploit the deployment of Node.js loaders and advanced stealers that scrape live Linux memory to siphon off the very keys to the cloud.
The overarching takeaway here is that the traditional concept of a security perimeter is dead.
It's gone.
It is.
Yeah.
You can build the thickest vault door in the world at your network edge, but if an attacker can forge a digital notary stamp to compromise an internal IT management tool, they don't need to break through the vault door at all.
They just steal the developer session token and ask the AI assistant for the combination.
It is a completely transformed landscape. The attackers are moving horizontally, operating quietly within normal startup scripts, and they are targeting the specific tools that hold all of our contextual data.
If there is one final thought to leave you with, it revolves around the immense trust we are placing in these new workflows.
Yeah, we are increasingly relying on AI assistants to write our code, to manage our cloud deployments, and to analyze our most sensitive corporate data.
And threat actors have clearly realized that these AI tools hold the master keys to the modern enterprise.
Which means we have to ask ourselves, are our AI assistants quietly becoming the ultimate single point of failure?
Wow.
If an artificial intelligence is helping to run your infrastructure, who or what is guarding the AI's login?
Because if we aren't careful, we might just be building a brand new impenetrable bank vault and completely forgetting to check if the AI assistant left the back door propped open. Keep questioning the architecture around you, keep learning, and we will catch you on the next deep dive.